Okay. Um, Laplace transform and transfer functions. What's Laplace transformation? Well, Laplace transformation is a kind of transformation similar to other transformations you have studied. Fourier transformation. You might even have seen Z transformation. So Laplace transformation is aiming to substitute a differential equation with a much simpler equation, which is algebraic equation, and solve that. So the way we use it, the reason why we use Laplace transformation is that we have differential equations which describe the behavior of a system, and we want to substitute that with something simpler that we can work with, and Laplace transformation can help us. So what Laplace transformation receives is a function of time. And what Laplace transformation creates is a function of frequency. So it receives a function of time and it spits out a function of frequency. The convention is to show the output of Laplace transformation with capital letters. So if I'm showing the input uh, of the Laplace transformation as f, small f, the output would be capital F. If I show the input uh, as g, a small g, the output would be shown with capital G. Notice that the input is a function of time and the output is function of something else. It doesn't have t anymore. The output is going to have s, which is frequency, and we have described it here. It's a complex number. If I take the Laplace transformation of a function, it gives me a new function. Now, if I take the inverse Laplace transformation of that result, it gives me back the time function. Notice that to achieve this output, to achieve the Laplace transformation, we can plug in our time function into this equation, which is an integral from 0 to infinity, and uh, manually compute the Laplace transformation. Okay, let's see two examples. I want to see the Laplace transformation of unit step and then this exponential function. Why is it called unit step? Well, this function has the value of 0 at t smaller than 0, and then it suddenly jumps into 1 when t is positive. So it's a step, and because this value is 1, it's called unit step. And then this exponential function starts, so plugging t equals to 0, I'm going to have e to the negative 0, which is 1. So it starts at the value of 1 and then gradually decreases, and then goes to 0 as t goes to infinity. So I plug in from the definition, I plug in the value of f. I'm just going to have 1 here because the integral is from 0 to infinity. So then I take the integral and I'm going to get 1 over s. So the Laplace transformation of step, unit step, is 1 over s. If I use e to the negative at, I can add the exponents and then I can take the integral and then substitute infinity, which results 0, and then substitute 0, which results 1 over s plus 1, plus a, sorry. Okay, so that's how you compute Laplace transformation. But for our purposes, we don't really care as much about computing Laplace transformation. That's a subject in mathematics. What we actually care about is to use them. So we have tables for Laplace transformation. It's called Laplace table, which we look at them, we look at the time function and then the equivalent frequency or Laplace domain value. So 1 becomes 1 over s. Wait a second. I just saw 1 over s. Let me go back. Wasn't 1 over s here for unit step? So now I'm saying if I have 1, it would be 1 over s. What does that mean? Well, what that means is that, let me go back again. Unit step was a function that had the value of 1 when t is positive and then had 0 when t was negative. That is what we mean in Laplace table. All of these functions have that property. What we actually mean by t is that it's a function that has the value of t, or ramp, when t is positive, and it has 0 when t is negative. What is this delta? This is called delta function or impulse function, which has the value of 0 everywhere except at t equals to 0. At t equals to 0, it's an impulse. It has the value of infinity, and the Laplace transformation of that would be 1. Another piece of Laplace table is describing the properties of Laplace transformation. So if I have a function f, and if I have the Laplace transformation of it written with capital F, I have these properties. Let's look at them. So the first one says the Laplace transformation of f of t plus g of t is f of s plus g of s. What does that mean? It means that if you take the Laplace transformation of the addition of two functions, that's equivalent with taking the Laplace transformation of each of them separately and then adding them up. So if you have two functions, if you add them up, you're going to get a more complicated function that might be more difficult to take the Laplace transformation. But you can take the Laplace transformation individually and then just add them up. What is this saying? It's saying if you have a number multiplied with a function, and then you want to take the Laplace transformation of that, you can just take the Laplace transformation of the function first and then multiply that number to it. For the derivative, if you have the derivative of a function and you want to take the Laplace transformation of that, you can just take the Laplace transformation of the function itself and then simply multiply with an s, and then subtract the initial conditions. Notice that this is the small f, so this is the time function, this is the frequency domain one. Okay, so this last property is very useful for us because it enables us to use Laplace variable as an operator. So anywhere that I see derivative with respect to time, I can just substitute that with an s. And anywhere that I see an integral with respect to time, I can substitute it with 1 over s. And that makes it very simple to work with time domain equations or ordinary differential equations, because it's normally very difficult to work with them, but now I can just substitute everywhere with s. Another thing to notice was the first two properties that we had in the table. So these two properties. These two properties mean that Laplace transformation is a linear operator, and they're very useful and they very much help us. Okay, let's see examples. I want to work with and solve these two differential equations. When I say solve a differential equation, what I mean is that tell me or write down for me what y of t is as one equation. So solve it means that write y of t equals to what? Okay, so what shall we do here? Well, I take the Laplace transformation of both sides. On the left-hand side, I have dy to dt negative 2y, and then on the right-hand side, I have 2 delta t. When I take the Laplace transformation of the left-hand side, I notice that I have linearity for Laplace transformation. So rather than taking the Laplace transformation of these two pieces added together or subtracted, I can just take Laplace transformation of the first one, Laplace transformation of the second one, and then add them or subtract them. Also, because of linearity, Laplace transformation of negative 2y of t is equal to negative 2 Laplace transformation of y of t. Okay, so what's the Laplace transformation of dy to dt? It's s y of s, and then subtract from it initial conditions, so y of 0. What's the Laplace transformation of y of t? Just y of s. What's the Laplace transformation of delta? 1. So Laplace transformation of 2 delta is 2. So I can factorize y of s from the left-hand side and then divide both sides by s minus 2. And this is s y of s. But that's not what I want. When I say solve a differential equation, I want to find y of t. So can you tell me what I have done here? Here I have taken inverse Laplace transform from the table. Look at here. If I have 1 over s minus 2, the inverse Laplace transformation of it would be e to the 2t. So I have 2 times e to the 2t. All right, how about this differential equation? Again, I take Laplace transformation from both sides, and I use linearity and follow the same steps, except now I get negative 3 divided by s times 3s plus 1. And I don't have this in the table. So how can I find y of t? I don't have anything, I don't have any result in the table for this more complicated fraction. So that's what we are going to cover later, probably in the next topic.